Okay, great. Let's start. So, my name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. And today I have the pleasure of hosting Professor G.P. Lee from UC Irvine. Professor Lee holds two appointments in two departments, electrical engineering, computer science, and medical engineering, and also in the materials and manufacturing technology. He holds key leadership positions at UC Irvine, including the Director of the Integrated Nano Systems Research Facility and also CALIT. He has served as the UC System-wide Chair of the Executive Committee for Electronics and Manufacturing Research and New Materials at the University of California from 2004 to 2006. Prior to joining UCI, he was with IBM's T.J. Watson Research Center. And when he worked at IBM, he worked in the area of VLSI technology with an emphasis on advanced bipolar technology, and he led a research and development team to transfer the technology into the production. He has served on roadmap committees, and Professor Lee has published more than 430 research papers. And in a plethora of topics: microelectronics, microwave circuits, microelectromechanical systems, IoT, data analytics for edge applications, etc. And he's also a fellow of the IEEE and the Asia Pacific Artificial Intelligence Association. He also holds 40 patents. So today he will talk to us on actionable intelligence-enhanced semiconductor manufacturing. Essentially, he will be discussing the reproducible fabrication processes and maintaining tool uptime, which is essential for efficient production in microelectronics. Professor Lee, the stage is yours. And thank you.
Thank you. Before I start, I want to take this opportunity to thank California Dream for hosting this technical seminar series. And I also want to take this opportunity to thank the audience for allowing me to exchange ideas with you. And my name is G.P. Lee, and GP stands for good person, very easy to remember. So in this presentation, I will cover three main topics. The first one, what are the AI infrastructure needed for manufacturing so that we can do AI model development. Second topic is how we develop the AI model in manufacturing environment and requiring minimum labor-intensive labeling of the data. And lastly, I will present the application of this AI infrastructure and AI model in three application cases. So based on my career over 40 years in semiconductors, here is my assessment of a current challenging in semiconductor manufacturing. Especially this is true for defense electronics. We are facing is small and medium volume production and with a diverse niche markets. Right? So under those operation conditions, typically in the fab, same pieces of equipment being supporting multiple process run. And also the wafer run lacking routine repeated process, unlike a TSMC running million wafer a month. Probably we will run maybe at most 1,000 wafer a year. So how do you really deal with this lacking of routinely repeated process to ensure we have a higher performance and yield in the manufacturing process? And because of this on-demand wafer run, the process control is facing drifting over time, especially related to the standard operation procedure, how we use the equipment and the process recipe, because it's in between the wafer run, there are other processes being performed. So those are the challenging issues in the small, medium volume production and niche markets. Similarly, because of the machine is now running 24/7, so we are facing equipment maintenance issues. And traditionally, in large volume production, they do preventive maintenance. For small volume productions, preventive maintenance could be very costly, so predictive maintenance become a desirable features. So how do we do that? And lastly, we also understand in the last 20 years, we are facing nationally lack of a skillful workforce. And especially in this generation of a data-driven manufacturing, Industry 5.0, including human in the loop for Industry 4.0. So under those conditions, now the future worker need to also understand the operation technology and information technology. So, and at the same time, we see the Internet of a Thing or industrial Internet of a Thing or AI for Internet of a Thing eventually lead to the digital twin for optimization in the virtual and physical world. So under those consideration of challenging in semiconductor manufacturing, one may ask a question, how can AI address these critical manufacturing challenges? Here is the solution we are proposing. We're proposing semiconductor manufacturing empowered by AI agents, very similar to the concept currently used in large language model. So for the small and medium volume productions, we need to do is a capture effect of a multiple process run on equipment via self-labeling data. So we do not require additional resources, human resources, to deal with this tedious work, and don't want to consume the precious time from engineer and technical staff to do that. And we can constantly update the process knowledge graph on demand so that there are more inside information to be provided to the engineers. And eventually we can lead to the dynamic process control, no longer standard operation procedure or process recipe based on the initial design. Now you can continue update to address the drifting of those process window over time in the small volume productions. For the equipment maintenance, we will be able to capture time information. This is a very unique currently when you look at majority of AI learning, information has not been captured about time. No one really understands the time's value in the how do you attract time informations. So in our AI model, we will be able to capture time information in terms of the runtime for the process, as well as the number of a run, and see how they can impact the SOP and process recipe. And this is via self-diagnosis at the idle mode of the equipments. Then the last piece is about scalable workforce development. So we have worked with a company and community college to develop AR and VR scalable training with an AI large language model to provide the initial learning. Then we leverage what we have done here in the part 1 and part 2 to provide contextual information for operation failure analysis so that it can be incorporated into the learning platform. Then eventually integration this IT and OT with the AI copilots for adaptive learning continue to evolve and can address individual workers' need based on their background trainings. So now let's see how we implement that. Shown here is the typical data flow in this generation of Industrial 4.0. So shown here is a typical envision in the data flow and to do the manufacturing, to support manufacturing. The first two is really about digitization of your lab or fab. So it's a computerization and connectivity in your fab. So this is the work being done by UC Santa Barbara, USC, and UCLA working together with the PDF to allow all the equipment's data captured by PLC through the connectivity to come up with a standardized data format for visualization purpose. So after you have captured all the data, now we want to do is what is happening. This is what currently being done by the Cal Dream Hub is a visibility of those what's happening based on the data. And the next step is how do you really come up with what is happening? So it's to provide deeper understanding so that we can be prepared about situational awareness. Eventually, with all the insight and intelligence, one will expect to have a self-optimization process recipe or standard operation procedure so that the system can be autonomously respond to the change. Right, so this is a very noble goal. And how do we do that? This is the task we try to perform in our AI enhanced smart manufacturing. So shown here is the smart manufacturing innovation proposed by one of Manufacturing USA Institute, SESME, host at UCLA. Shown here is the information flow for a given process, a piece of equipment, what kind of a PLC sensing you need to do, and collect the data, and how do you contextualize the data to really relate the data, raw data into information. And with the information, you can perform analytics to really provide the insight about what is really happening. And through the modeling, you can really create the intelligence to provide the feedback control to the equipment. But one thing is most critical, I believe, is humans should be in the loop. That's why I focus on Industrial 5.0. In addition to this information flow, now we have to have a smart worker at the center stage. And it is a key manufacturing asset to allow human intuition and human five sense to be incorporated in the entire information flow so that we can empower the smart worker with AI copilots and to really optimize the process. So how do we do that? So for a piece of equipment, the first thing we try to do is how can we really convert a piece of equipment into something we can understand in the information flow. So showing here is I'm using one example of a plasma enhanced CVD deposition systems. So as you know, for a given piece of equipment, here is a machine ontology. It has various components, has the heaters, has a roughing pump and mechanical pump or turbo pump, and you have a PC interface and so on, heater, RF generator, and so on. So those are the typical components presented by the machine ontology. So the equipment engineer now is going to convert this ontology into dynamic knowledge graph via standard operation procedures. And basically is to create a state machine based on operation of each components and in a sequential or parallel fashions so that we know which component can be turned on at what state. And so we can track the state. So this is the way we can digitize a physical world into the information flow as a state machine for a piece of equipment. So the next step that's observed in semiconductor manufacturing is more complicated than just a simple piece of equipment. And typical for manufacturing fab in semiconductor, it consists of tens to hundreds of pieces of equipment. They perform various functions. So how do we design such a cyber physical, human, and environmental system? Because when you are dealing with different pieces of equipment for an integrated process, and the wafer will flow from one piece of equipment to the next, and to the third one, and come back to the first piece of equipment to do litho again, and so on. So there are a lot of interaction happening in entire information flow. So here, the observation we have is the entire semiconductor manufacturing is truly based on interactions. The interaction consists of three major elements. One is the interaction between the human and the material. basically this interaction is human knowledge to design the process recipe and what is the condition for the temperature and eye power so that you can do the deposition and what kind of gases you need to do and so that you have a better deposition rate. So this is an interaction piece. And the second interaction piece is between the machine and materials, because you know what kind of gases need to use, and you select what kind of machine to be used. It's just a CVD deposition or PCVD depositions. So it has a different conformality, different deposition rate, and uniformity, and so on. Right. So that is the interaction pieces, and selecting the control of the equipments and materials. And the last interaction is human with a machine, which is we are providing the command through the standard operation procedure to activate the machine at the different steps so that it can perform this interaction between material and machines, right? So the worker also have interaction with the environment in terms of the scheduling, when to do what for the wafer run, and also has an interaction with the world in terms of knowledge, experience, and planning. Right? So this is a really from the internet. You can download the information, or you can use a ChatGPT to capture some of the information, allow you to really understand the implication of different interactions. And as a result of the interactions, it will have a product and byproduct. Product is the high performance, high yield semiconductor chip. And byproduct is the chemical waste and greenhouse gas emission and impact on the environment and so on. And also here are the machine has the implication on the maintenance, energy consumption, and so on. So this is really entire ecosystem in semiconductor manufacturing. And the key action is the interaction among human, machine, and material. And it's an interaction with environment in terms of the product and byproduct and the energy it consumes. Right? So with that in mind, this tells us there is a way to create an AI model based on the sensor data from this ecosystem so that we can have a holistic view of entire semiconductor manufacturing. So before I dive into that, let's recapture the feature in semiconductor manufacturing. So the semiconductor manufacturing functional module process, typical as we define in CalDream, it has a litho process, deposition, etching, and post-process metrology, measuring uniformity, thickness, and the sidewall profile, and so on. And typical, when we perform those processes, we use the inside data from the inside the machine, push the data out from the PLC data. And also there is outside data from the environment, the power or the image or video, like the security camera, you can see how human interact with the machine and whether they perform the right process. And second observation in the semiconductor manufacturing is there is a rich domain of knowledge in terms of process recipe and standard operation procedures and the post-process wafer characterizations. This is how the process engineer develop the process recipe and probably run a few wafer run to really define the process window and what is the process condition to produce a chip. And those results are based on statistical result, and it's more like you can achieve a stable process run with a standard SOP and the process recipe, and technical staff can follow that to produce the wafer with some percentage of yield. And by characterizing the wafer process, we can continue to improve. And also, in semiconductor manufacturing, for the equipment, they are two states. One is active operation, which is to perform the process recipe, and this interaction happen among equipment, material, and worker, follow the process recipe and SOP. And this defines the process integrity and whether we can have a high yield. The second one is the equipment is not running for the active operation and is in the idle mode, or the other way we say is a sleep mode. Under this sleep mode operation, the interaction is only between equipment and the material residues. And material residue is from the prior active mode operations. And the interaction between equipment and material residue from the prior active operation will have implication on machine integrities. So this really gives you a hint how we can use active mode and idle mode alternate and create a state machine to do the self-diagnosis to understand the integrity of the machine. And from integrity of the machine can also have implication how that may affect the active operation, because there are some residue in your equipment and they may affect active mode operation in terms of interaction between equipment and materials. So this is the very basic concept we are proposing for realizing this AI model. So how do we do that? So what we propose is so-called the interactive causality engine to develop the AI model. So the interactive causality, as I just defined, is based on the interactions. So we have here is the human knowledge graph. Human knowledge graph is about how a worker working inside the fab using equipment and typical their motions, key in, and their hands or leg movements. It's categorized the interaction of human and machine. And material is really defined the knowledge graph from the recipe, and the machine is the standard operation procedure, as I mentioned earlier. And their interaction will produce some output product for the deposition or etching or litho pattern definitions. And so from the domain ontology and the dynamic knowledge graph, following the SOP and recipe, now we can really define a self-labeling adaptive learning under this interactive dynamic knowledge graph domain. So before the deployments, one can do is to identify machine learning question with interactive objects, what we are interested in. Once we know the interactive object, now we can select the sensor modality. What kind of sensor should be used to relay the interaction between one to the others? And then once we have that, we can, from this relationship, we can define from the sensor, we define the state and identify the causality between the cost of the machine and how that change the material property effects, right? So identify the causality, and this is really the static model. And through this interaction, the causality, we can determine the interaction time. Say, for example, if you do deposition of 30 minutes under the plasma power of 100 watt or 50 watt and SCCM or 50 or 100, it will give you different interaction time. Then from the measurement, we can really get a temporal causal model in this interaction. So this is how we determine the test model. Once we have that, based on the prior knowledge of SOP recipe and the human movements, now we can deploy the system. And in the deployment phase, all the cost data is coming in and to be compared with the task model to see whether it show up as an effect. If there is a deviation, now we can label the data whether that's within the model, because originally the dynamic knowledge graph may not capture all the interaction nodes. So when there is anomaly, the anomaly can be selected into label data set and see how frequently it happens, so we can continue grow the knowledge graph, so that this is really adaptive learning. So you can imagine when we do a flight simulator, you need to have millions of possibility for the values. So it's very hard to predict. So what we are proposing here is, in terms of processing equipment, it's like a flight simulator. We start with the knowledge graph from the engineers. So we have simplified number of nodes for the parameter in AI learning. And by labeling the data, sub-labeling, and we can see repetitive those anomaly to generate additional knowledge graph. So this is really regenerative knowledge graph, right? So allow us to discover the growing, emerging node in the process as a result of some of the condition change. And this has never been done for the first time. At the same time, because we are able to attract the time information now, the time information become another asset in manufacturing. So that's a deeper dive into the sub-labeling without experts. How does that happen? So as shown here, we can, because we have a translate the ontology into dynamic knowledge graph, we can define the state machine. And so what we have is, by defining the threshold, now you can see is when there is state observed effect change, and above the threshold, we say that is a cause event. Then see what is the effect we can measure or observe. And by noticing the difference between the cause state and effect state, we can define the interaction time, right? So this is how we define the interaction time, and using the sub-labeling. And because the state is the simple thinking here is, let's put an analogy to humans' health conditions. We can measure the temperature. You can say every 10 seconds you do a sampling, it's an event, right? So you see the temperature, and now it's a 36.5 degrees C or 37.5 degrees C. It's a random, right? So every 10 seconds there's an event, you see the data. But when you see the event happen is when the temperature is greater than 38, you know it's something is triggering. That is the cause. Now you're looking for the effect. If someone is coughing, or that is an observed effect, right? So, and then what is the incubation time? That's interaction time. This is just an example how we do the modeling of a causal time lag to allow us to do sub-labeling without the expert by using the stream of data. I'm using two stream of data as an example. In real world, in our application, this stream of data is coming from multiple variables, hundreds of them, right? That is a domain we're dealing with. Then, so in order to really ground you with understanding of this causal sub-labeling technique, I think it's most of a process engineer is very familiar with the so-called process development with design of experiments. So the cause state is a PLC sensor data. And we see is what is the pressure, what's the temperature, what's the R power, what is the gas flow rate, what are the gases, and so on. Those are just 5 different streams of the data. And the effect is we're using online metrology detector to measure uniformity, thickness, and sidewall, vertical sidewall. And so we can model this causal time lag, right, based on the SOP. This is, I think most of process engineers understand that. But under the AI model data stream, without the expert involved for self-labeling purpose, now we can establish interactive causal events. The cause event is equipment is in the active mode or idle mode. So they are state change. And whether there is a human machine interaction because of something is not proper done, and humans step in or observe something new to provide that information. and also the PLC state and SOP event and so on. The effect is the external to the equipments from the environment, like the power current or the image data from the security camera or from the new sensors and PLC state, because this cost due to something else can also impact the PLC and then online metrology. Now, when we are dealing with the modeling of causal time lag, now is the interaction time is based on the SOP, recipe, and number of wafer runs. So it's not only the SOP and recipe, the number of wafer run, because the wafer run could be executed at a different time, right? So there's a different time lag. So those are information we want to capture as a way to really provide the self-labeling. Okay, so by doing that, we can develop the AI model in cyber physical system. And this, because we are using the interactive causality, that interaction causality really providing us with contextual learning. The data now is not just raw data, it's not just information, it has contextual information, the causal relationship, right? And it's based on the interactive relationship we define in the dynamic knowledge graph initially and grow over time when we run the wafer run. And it is really also based on rich domain knowledge from the recipe and SOP developed by equipment engineer, by process engineer, and to identify sensor and classify their data for doing the machine learning and to create an AI model. And one thing we also notice in this defense electronics, usually we have very limited pre-allocated data set for model training in diverse the cyber physical system environment. So because of this interactive causality can allow us to shrink the number of data requirement initially to allow us to grow by self-labeling technique. And also this AI model development is done by ingestion of a time series data, right? So we are doing every few seconds, spit out the data from the IoT sensor, from the PLC, and so on, image. And also possible data shift because of process change from prior. So we can do that to update AI model at the edge in dynamic environment. And also, once we have this updated AI model with insight, and depending on workers' background training, it can be personalized to really create an AI co-pilot for the human working inside the fab. So now with this sub-labeling technique, let's look at how we can look at the data stack to do the machine learning. And showing here is an integrated wafer process workflow, right? And so this is a wafer, it goes through the modular process. Modular 1 and modular 2 is say this is a litho process, this is the etching process. Litho process, you have a step is photoresist coating and baking and exposure and so on, right? So the input information is which company are doing, asking for that process and what wafer lot, and within the wafer lot, what is the wafer number, and what is the recipe used, and what is the mask and the timestamp, the information when that is executed, and what are the recipe parameters. And the output is a physical measurement for those modular steps. So now what we try to do here is based on each modular, we can create machine agents to analyze the machine. And also we can look at is a modular interactive causality agent, is how one process can affect another modular process, or within a modular process, how step 1 may affect step 2. That is an interactive causality. We try to extract from our data stack using our sub-labeling technique and interactive causality. So here is the example how we are dealing with a machine agent to allow us to find the anomaly in performing the task, as well as to determine remaining useful time of the machine, right? So this is a step input and to the machine and step output sensor data and go through our machine agent learning, as I just mentioned, interactive causality and sub-labeling. So we can detect the deviation and detect out the range and so anomaly. Then we can also compare with the historical output of a machine agent in machine A, right? So here is the input to the machine agents, right? The time gap from the last step and output of the last step machine agents. So this is a interaction is built into our machine agent for the model developments. Then now you can see is a machine learning information flow of a modular process. Now you have machine agents for deposition, for litho, for IE etching. And so now how one modular process can affect another modular process and so on. So now we can look at the interaction within an integrated process among different modular. Right, so this is really taking a holistic view of an integrated circuit manufacturing because it consists of so many steps and we partition them into module and each module's interaction can be developed through this interactive causality. And so this is how we are using this machine agent as we present previously for deposition, litho, and IE, and for the machine agent output anomaly to have the interactive causality agents to update the knowledge graph as well as to identify the new causal time series between the wafers and as well as within the different modules. So this is how we extract those information from data stack. So with that, now we ask ourselves, now we understand how we can do the AI model development and the data stack for the machine learning. So how do we select the sensor for doing the machine learning, as I mentioned earlier, for the interactive causality? So the goal here for the sensor selection is to complement the human five sense and human intuitions. So typical we have existing is a timestamp PLC data log used in automation control, right? So this is based on active process control to meet the process recipe and SOPs. And video camera is the security camera inside the fab. Is to me, it's like a wingman observation, the interaction between human and machines. Then in addition to those existing setup, we introduce additional information about the power and current monitor. And this electricity disaggregation of various machine components, because this can tell us for a piece of equipment how each component may gradually wear down and the electricity consumed by those components may change. And it may tell us whether the RF tuning is out of tune, so the input power is increased. And in addition to the traditional security camera, we introduced one of the very unique spectrally resolved imaging camera. It provides spatial and spectral information in semiconductor manufacturing for small scale productions. And later I will show you how important it is. And also the information about timestamp of the wafer lot number, process recipe, SOP, because all of them are information we need to use to me, this is also sensor data, is a human knowledge sensor data, so that we can really capture the information we need. Okay, so this is a new spectral image So traditional, this is a black and white camera. This is today's iPhone and 3-color camera. And this is a multi sensor camera. So you use a filter to have different wavelengths. So the hyperspectral imaging will provide us with every 2 nanometer resolution in spectrum and get the image. So this is a hypercube information about the material processing happening inside the reaction chambers. So once we have that, as this additional sensor, now let's see the machine learning pipeline, how we do that. I'm using one example of the RE etching system we perform in Triumph systems. So we know before the wafer processing, we do oxygen cleaning of the chambers, then start wafer loading through the load lock and perform executing the etching. And when it's done, and wafer unloading, and you perform another oxygen cleaning and machine into the idle mode. So this is active mode, this is idle mode. So in following the workers' interaction with machine through the SOP and the recipe interaction between machine material happen in the etching. So now we have the data collection is a PLC data from the equipments and also external environmental data power fit into the equipment. Also the hyperspectral image to observe what is happening inside the chambers. Then after wafer loading, we do the metrology characterization and also perform the standard oxygen cleaning. Okay, now after you have the data, based on the information you have here, you can do the feature extraction using the causality we have to look for the deviation and anomalies, right? So once we have that, combining the inference among them, we can identify degradation pattern, estimate remaining useful time for predictive maintenance, as well as identifying cause and effect, suggest recipe adjustment for process optimization. And all the information can be used to upgrade the knowledge graph. And this is really the machine learning training updates. And this is the infrastructure of the AI infrastructure in manufacturing. Very different from currently the generative AI. We have this additional data collection interaction in addition to simply the computation resources. And this is how you can set up an example for the hyperspectral camera and the power meter connect to your process equipment and the PLC data. And this is the data stream and how we perform the machine learning pipeline. Now I'm going to give you 3 examples for the application. First is AI-driven plasma process monitoring. Right, so here is a typical background information about reactive ion etching, and the plasma is used in deposition etching and surface activation. And equipment performance degrade over time due to the residue buildup and component wear and electrical drift, high power. Traditional monitoring is a basic data, and it cannot capture the subtle change. And maintenance practice is a schedule-based or manual judgment by the engineer, so may result in over maintenance or unexpected failure. The quality issue is a positive drift may go unnoticed, and inconsistent result reduce wafer yield. Right, so those are the typical we heard from working with engineers. And so, what are the opportunity here? So because of the modern plasma tool generate a large volume of heterogeneous data, unstructured data, and the signal are noisy, weak, correlated, and buried in the background drift. And traditional rule-based systems struggle to interpret complex pattern, and human operator cannot manually track all channel in real time. So many different stream of data to track that is very hard to do. So the opportunity is AI-driven productivity enhancement is real-time monitoring continue analyze data from PLC log and IoT sensor, as I mentioned, and perform anomalous detection and trend analysis so that we can do predictive maintenance, increase reliability and uptime of the equipment. Right, and this is the system we use, as I mentioned earlier, for this prototype demonstration of RE systems. So showing here is a hyperspectral image captures. So this is it's an image. So we're looking at the wall of the chambers, and this is a wall chamber. This is in reference to the wafer surface towards the anode of the electrode of the IE systems. And so you can see here is along the wall, you can see the plasma uniformity and the spectrum. As for example, at this sampling point, you can see the for the given oxygen conditions, the O2 and the O plus, and so on. And the reason why we use a hyperspectrum is this is a typical spectrum information of oxygen. The intensity of the spectrum depends on the eye power and depends on the flow rate of the gas as expected. And also the spectrum change depends on the gas you use. So that's why we use a hyperspectrum to look at the uniformity of the plasma reactive ion gas inside the chamber and whether there are any residue can be detected, right? So oxygen cleaning process is used for the self-diagnosis of the IE system during the idle mode, because the O2 cleaning process to do machine characterization is the recipe is simpler and is standard and only related with atomic oxygen. Any new plasma peak will be related to the contamination residue inside the chamber. That's variables. So here we pick two wavelengths as way to do the analysis, O2, plasma, and atomic oxygens, because they have a high intensity. So showing here is we are focusing on one point and look at the time-lapse data of this oxygen and O2 plus. O2 plus. So what you can see here is initially there, the O2 plus is performing the etching, and when that condition is improved through the cleaning process, the yield of the O2 plus is reduced. Okay, so this is really telling you from this time information how you need to design your recipe for the cleaning to ensure the integrity of the machine so that your process integrity can be maintained. Right, so now we can do the mapping along the wall of the chamber. So you can see here, this is at the surface of the wafer towards the anodes. So what you can see here is at a different location, it has a different plasma intensity. Right, so now you can look at either across the wafer or along the chambers, give you the uniformity information after any given active process. And by using the power meter, this is just a simply clip on, you can really look at to desegregate the electricity from the up generator, pump, PLC, PC, and so on. So we can see the plasma instability, component degradation, and unexpected load change or arkings. So showing here is by doing the energy desegregations, and we can see is this is a initialization and to have the gas flow, and this is RF power turn on, then we reach a stable state, and this is a power off. And then you can do the synchronized data for the hyperspectral image to see at the different time how the spectrum shift and whether the part, for example, this is plasma turn on, you can see how long it will reach a stable state and whether this condition change over time as a result of the process chamber change. So here is another example, the e-beam deposition system. And we can first categorize for the e-beam deposition and see how the process chamber exposed to different environmental condition may impact the leak up rate of the chambers. And also showing here is how different deposition aluminum oxide, aluminum or titanium, and change the leak up rate and pump down rate of the chamber so that we can predict the integrity of the equipment when we need to do the predictive maintenance. And this is done by self-diagnosis. As I mentioned earlier, we divide into sleep mode, the idle mode, and active mode. And going through this machine learning in both sleep mode and active mode. And we get the information about from the predictive about the predictive maintenance of the pump, and we know when we can really turn to really slow down the pump speed to save energy and also provide actionable intelligence to the workers. And this is done by doing the comparison of the data with the failure analysis of the fishbone. So give us that update information. So the third one is AI-driven scalable workforce developments. So this is using this interactive causality, and we use the machine learning, so-called the open post, by extracting the skeleton of the human working inside the fab and their interaction with the equipments, so we can predict whether they have the load the wafer properly because of orientations, whether they follow the sequence of event to operate the equipment, and whether they are using the right SOP or a recipe, and as a way to capture the mistake they might have made. And so here is just with 100 data sets. Original is 85.7%. After 200 runs, after additional 100 runs, it can give you the accuracy almost 98%, 99%. So can really capture the interaction between human and machine. And from the diffusion pump, and it has a first stage and second stage. The time lapse also give us the information. We can track how the cleaning, how the changing the oil of the diffusion pump may change. There's a time lapse as a way to do predictive maintenance, right? And this is really based on the energy disaggregation we're able to do. And we also convert the whole thing into virtual reality, and with the AR, VR platform, and together with the contextual information for virtual training content. So this is really scalable. It can really allow people to experience sort of in virtual environment to experience just like a flight simulator without flying the airplanes. So in summary, a worker-centric actionable intelligence AI edge system, cyber physical human environment system, has demonstrated to extract time information in addition to contextual sensor information for developing adaptive SOP and process recipe, as well as the equipment predictive maintenance in semiconductor manufacturing for the first time. And AI infrastructure, sensor, IT, and computation at the edge distill AI model based on interactive causality, and their application are presented in this cyber physical human environment system. And AI-driven workforce development platform is also presented. So I want to thank you, and we welcome opportunity for collaboration. Thank you. I'm sorry I took longer than 5 more.
That's okay. Thank you so much, Professor Lee. This was an excellent presentation with a lot of details into it.
Yes.
The amount of details, it's incomprehensible that you have done all this. Thank you so much. And
thank to Dream's support of our project.
So let me ask, any questions from the audience? Oh, there is one question here in the chat. Dr. Sivai Sung is asking a question. Ultimately, what will be the values of humans in the loops?
Okay,
So
so human,
if everything is AI, what is the value?
I
So
think is the major value if you petition the entire cyber physical system. It consists of data rich, data rich virtual environments, and data rich means content. Machine is very good at the content because huge memory. And human is not good at the content, but is good at contextual information put into the sequence event. So the causality is really the tool human employee. Right? How we learn as a baby to recognize someone is a mom or dad, we are making noise. Mom, 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 right? So, and your mom probably pat your head with that's a labeling technique. After several times, you say, "Hey, I like that pat." Okay, and that is the labeling. It's human learn is based on contextual information, not based on the content. Okay, and machine AI is right now is primarily large language model is content driven. So the combination of these two will really make the system perfect. So human in the loop in this condition is since human can be assisted by the AI, at the same time, human has five sense and intuition, the common sense. So human input can really also augment the learning in AI. And that is something we try to capture in this platform. So always there are information we can put in, right? So that's why when we look at human machine interaction, is someone step in to say, you need to change the recipe. Why? Because that is a human knowledge. So there is event happens, right? And you can capture the human knowledge at that instant. That is how you can update your knowledge graph.
thank you. There is also another question, and the question is, what's the difference between traditional feedback loop control versus agentic AI system?
Okay, so the traditional feedback loop control is based on the state machine, static. That's a traditional static,
Yeah.
right?
Mm.
So, and in this AI-based feedback loop is based on because our ability to extract time information because the equipment changing over time, right? Because of the chamber contamination. And so day one and day 100, the chamber condition may be different. And in between, someone may clean the chamber. So every time the condition is different. So this is a time-based dynamic adjustment of feedback control is what we are able to do with this AI-based control loop.
Mm. And there's a follow-up question there. I mean, does the system improve itself automatically based on the accumulated knowledge? It can
Yes,
actually, probably. Yeah.
I think it's based on two things. One is existing knowledge, right? So like a SOP or recipe, usually you can get that from large language model, right? From all the publication or from the menu or from the local experts, your recipe. And the second thing, as I say, because this interactive causality with sub-labeling allows us to grow the knowledge graph to discover the new interaction nodes. And that interaction node can be incorporated into SOP or recipe. And this
Yes.
has not been done. And we can do
Yes.
that.
Yes. There's also one more question, which is on Exensio software. Have you used Exensio software? Is the question in implementing the vision.
So the software, as I just say, in machine learning, primarily the challenge is the data structure, how you use the
Yes.
data, right? So
Yes.
once you have that data, then in terms of machine learning, the algorithm, machine learning algorithm, we use many different methods, regression, linear regression, or using convolution neural network. And because of the reason why we are able to deal with the edge, not relying on the huge computation resources. Initially, when we developed the model, it's a sort of a large language model in cloud. Then you can really deliver that to the edge. And the edge is really continue to evolve, taking in the data, and that number of parameters need to be analyzed. It's dropped from billion to millions. So the local computation resource can be reduced. The need can be reduced.
Yes, thank you. We are 4:02. So quickly, next week's seminar will be given by Austin Minich from Caltech, and here we have a series of upcoming seminars as well. Please stay tuned. Thank you so much for attending. Once again, thank you, Professor Lee, and thank you, everyone. Bye.
Thank you.